So in the first lecture, we have seen that it's impossible to define the function in all subsets of R which fulfill certain properties. So as I said at the end of this first lecture, what we will do is to try, starting from a definition of a function on the intervals, try to extend it to the largest possible set, keeping the properties we wanted. So today what we'll do mainly define some notions of class of sets, obtain certain properties of these classes, and then start our route in our way to the definition or the extension of these functions. So I will start with some definitions, and all these definitions are based on these intervals. So the first one will be, well, let's consider a set omega. Of course, you can think for the moment that omega is just R. And so let's recall that we represent by P of omega all the subsets of omega. So let's say that we have a class S, which is a subset of, so it's a family of subsets of omega. We will say that this class S is a semi-algebra if it has three properties. So the first one is that we will require the set omega to belongs to S. Then the second property will be that the family, the class S, it's closed by finite intersections. So we will require that if a set A and a set B belong to S, then A intersection B also belongs to S. And then if you think of intervals, so let's say that you take an interval A, B. If you take the complement of this interval AB, you don't get an interval, but you get a union of semi-infinite intervals. So our third property will be that, well, if I have a set A which belongs to S, then the complement of A can be written as a finite union of elements of S. So what we will require is that for all sets A in S, there exist sets E1 up to En in S, such that A complement can be written as a disjoint union of these sets A. So a family S which has these three properties will be called a semi-algebra. Let's see an example. As I said, what we have in mind are the intervals. So let's take omega to be R, and let's consider the following class of sets. Well, we need R to belong to the class, for the class to be a semi-algebra. Then we would like to consider the class of intervals which are, say, open on the left and closed on the right. So let's take A smaller than B, A and B in R. And to these sets, we will add the semi-infinite intervals. So besides that, let me include in this family the sets the intervals minus infinity to b, where b it's an element of R. And in the same way, let's include the interval a to infinity for a in R. And just to make sure that we are considering the empty set, let's include the empty sets in our collection. So let S, so I'm defining S as the class of sets which include all the sets I just described. And what I claim is that this class of sets forms a semi-algebra. This is very easy to check. So we need to check that the three properties of a semi-algebra hold. Well, the first one is that the set omega, which is here R, belongs to the family, but we included R. Then we need to show that this class of sets it's closed under intersection, and it's easy to check that if you take any of two subsets in this class, and the intersection will also belong to the set. You see that if I take, for instance, two intervals of this type, if I take the intersection, it will be either empty, which is an element of this set, or an interval of this type. And in the same way, if you take intersections of any of these two sets. So the second property of this semi-algebra, it's also fulfilled. And the third one requires that the complement of a set in this class can be written as a finite union of elements of this class. And this is clear if you take, for instance, the interval AB. Well, it's clear that the complement of the interval AB is just the set minus infinity A union B infinity, so that you're writing the complement of this element as the disjoint union of two sets which belongs to this class, right? The first one, it's an element of this class, and the second one, an element of that class. I leave to you to check that the complement of the other sets are also elements of, can be written as the union, a finite union of elements of this class. And I leave to you also to check that if you take, instead of R, you take R square, and instead of these intervals, you take rectangles of the form A1, B1 times A2, B2, with the natural extensions to semi-infinite interval, so that these class also form a semi-algebra, and you can extend that to any finite dimension in a similar way. So we have here an example, several examples of semi-algebra, and it's in fact, actually, these examples inspired the definition of a semi-algebra. It's by studying the properties of this class of sets that lead us to the definition of a semi-algebra. So I hope that the definition of a semi-algebra is clear to you at this point. So the second definition which will be important will be the definition of an algebra. So again, let me take a set omega, all the subsets of omega, and let me take a class of subsets, which I will now call denoted by A. I will say that A is an algebra if the following properties hold. Again, I will require that omega, it's an element of the algebra. We will also require that now this family A, it's closed by intersection, by finite intersection. So let's assume that AB belong to A. I will require that the intersection between A and B, it's also an element of A. And now we will require more about the complements. We will require that if A it's an element of the algebra, then the complement of A it's also an element of the algebra. So here is the difference between algebra and semi-algebra. While for semi-algebra we are requiring that the complement of a set in the semi-algebra could be written as a finite disjoint union of elements, here we require a stronger condition. We require that in fact the complement belongs to the algebra. So here is the definition, and it's clear. So let me just make a very simple observation, is that any semi-algebra, so if A it's an algebra, then it's clear that A it's also a semi-algebra. And very soon we will observe that we can speak about algebras which are generated by semi-algebras, and we will be able to describe precisely the sets of an algebra generated by the semi-algebra. But before I do that, let me define a third object which will be important. So here is a third definition, and this is the definition of sigma-algebras. So I will say that a family F of subsets of a set omega is a semi-algebra if it has the following three properties. Again, we will require that omega belongs to the family, but instead of requiring the set F to be closed under finite intersection, we will now require the set F to be closed under countable intersection. So I'm assuming that if AJ belongs to F for family, a countable family of sets, then the intersection of all AJ belongs to the class F. While we'll keep the third property, which is that if a set A belongs to the class F, then the complement of A also belongs to the class F. So we'll say that a family of subsets of some set omega, it's a sigma algebra, if this class fulfills these three properties. And again, it's clear that if F is a sigma algebra, then it's an algebra and it's also a semi-algebra. So we have here an increasing set of more and more restrictive conditions. So semi-algebra, it's weaker than algebra, which is weaker than sigma algebra. So now that we introduced these notions of semi-algebra, algebra, and sigma algebra, we will investigate the relation between these concepts. The first observation, it's a very simple one. Consider a set omega and consider a family A alpha of algebras of sets of omega. So each A alpha is an algebra of subsets of omega. And this index alpha belongs to some set I, and I won't put any assumption on I. I can be uncountable, for instance. It's any set. So we have a class of algebras indexed by some set on which we do not assume anything. And my claim is that if I take the intersection of all these algebras, well, this intersection is an algebra. So to prove that this class of subsets of omega is an algebra, I have to check 3 properties. So let's check these 3 properties. The first one is that omega belongs to A. Well, but this is clear because since A alpha it's an algebra, A alpha must contain omega. And therefore omega belongs to any of this class, therefore it belongs to intersection, and intersection is just A. So the first property of an algebra, it's fulfilled. Now let's prove the second property of an algebra. So let's fix a set A and a set B, which belong to A. Well, since A belongs to A belongs to each of these algebras. And the same thing is true for B. Since A and B belong to A alpha, and A alpha it's an algebra, the intersection of A with B also belongs to A alpha. Since the intersection of A and B belongs to A alpha for any alpha, the intersection belongs also to A, and we just proved that the intersection of A and B belongs to A, which is the second property of an algebra. Finally, we have to prove the third property. So let's fix a set A in the class A. Again, since A belongs to A, it belongs to each of these algebras A alpha. By the third property of an algebra, the complement of A belongs to A alpha. This is true for any alpha, so the complement belongs to A. And we just proved the third property of an algebra. So we just proved that this intersection is indeed an algebra. So this is my first observation. Now I will make a second observation that the same claim holds if I replace algebra by sigma-algebra. So let's assume that we have a set omega and we have a family of sigma-algebras of subsets of omega. Right? So now I claim that the intersection of all these sigma algebra is a sigma algebra. Well, let's prove that this intersection is indeed a sigma algebra. We have to show that omega belongs to A, but we already proved that in the sense that, well, if A alpha it's a sigma algebra, it's an algebra, and we prove that intersection is an algebra and therefore omega belongs to A. Or you can just repeat the arguments I used for an algebra to prove that in the case of sigma algebras, indeed omega belongs to A. So that's very easy. So difference occurs in the second property because instead of proving that A is closed by finite intersections, we need to prove that A is closed by countable intersections. So here we have to consider a class of sets AJ which belongs to A, and we have to show that the intersection of these sets AJ belongs to A. But we can apply essentially the same argument. Since Aj belongs to A for any j, these sets Aj belong to A alpha for any alpha. Since A alpha it's a sigma algebra, the countable intersection of Aj belongs to A alpha for any alpha, and therefore belong to A, which is what we wanted to prove. So the second property of sigma algebra is fulfilled, and the third one can be proved as in the case of an algebra. So in conclusion, what we proved is that if I take any intersection of algebras, I get an algebra, and if I take any intersection of sigma algebras, what I get, it's a sigma algebra. Well, now we can use these facts to introduce the notion of an algebra generated by a class of sets. So again, let's fix some set omega. Let's consider the subsets of omega, and let's consider a class C of subsets of omega. I want to introduce the notion of the algebra generated by this class C. This algebra fulfills two properties. The first one is that it contains C. And the second one is that if I take another algebra, say that B, it's an algebra which contains C, so if B it's an algebra and B contains C, then B contains A. So the algebra generated by the set C is an algebra which contains the set C, and it's the smallest algebra which contains C, because if any algebra contains C, it must contain A. So what we will call the algebra generated by the class C is the smallest algebra which contains the class C. And what I need to show is that such an algebra exists. And this is very easy. Well, let me take as A alpha all the algebras which contain C. So I'm just considering all algebras of subsets of omega which contain C, and let me take the intersection over all these algebras. For instance, this class is certainly not empty because one algebra which contains the set C is just the class of all subsets of omega. I leave it to you to check that this is indeed an algebra, and it's clear that it contains C. So I'm taking an intersection over all possible algebras which do contain C. We just proved that this object, which I will call A, it's an algebra. It also contains the set C, because each of these algebras contains the set C. So it's clear that A, it's an algebra. This is what we proved 2 minutes ago. And it's also clear that A contains C. Now we have to check that A is the smallest of such algebras. But this is also clear. Let B be any algebra which contains C. So B, it's somewhere here. It's an algebra which contains C. Since A is the intersection of all these algebras, A is certainly contained in B. So B contains A. Therefore, the algebra I just constructed is indeed the smallest algebra which contains the set C. So, I just proved that there exists indeed the smallest algebra which contains a class of set C. Observe that I didn't do any hypothesis on the class C. It's any class. And what I claim is that the same argument applies to sigma-algebra. So if I consider a a class of set C, so a class of subsets of omega, I can define the smallest sigma-algebra which contains the set C. Right? So I want A to be a sigma-algebra now, which contains C, but I want also A to be the smallest one. What does that mean? That means that if B is a sigma-algebra, and if B contains C, I want B to contain A. And how do I do that? Well, I just repeat the same argument. I consider here the class of all sigma-algebras which contain the set C, the class of subsets of omega C. And I define A to be the intersection. We have seen that A is a sigma-algebra. Since A alpha contains C, A contains C. And any sigma-algebra which contains C must contain A because it belongs to this intersection. So we can also speak of the sigma-algebra generated by a class of sets C. Again, observe that we didn't make any assumption on this class C. So these concepts will appear systematically. I will be systematically talking about the algebra generated by a class C or the sigma-algebra generated by a class C. And now I can reformulate one observation which I did at the beginning of this lecture, which is the following, and which will be very important. Let's assume that C is a semi-algebra. We will see in a few minutes that the algebra generated by a semi-algebra, it's very simple, in the sense that I can express exactly what are the sets which belong to this algebra. We will show that all the sets which belong to the algebra generated by the semi-algebra, they can be written as finite unions of elements of the semi-algebra. So we have an explicit form for all elements of the algebra generated by a semi-algebra. This is not the case of the sigma-algebras. We have no idea of what are the sets in the class, in the sigma-algebra generated by a semi-algebra. We have no expression to describe these sets. We have no explicit formula for these sets. And this will be one of the major difficulties in extending the measure from the semi-algebra to the sigma-algebra generated by the semi-algebra. This point is very important. You have to understand that proving that certain property holds for all the sets of the sigma-algebra generated by the semi-algebra requires an argument which does not rely on the fact that you have an explicit expression for the elements of this sigma-algebra. And this is a very important point. So up to this point in this lecture, I defined what is a semi-algebra, an algebra, and a sigma-algebra. And I also introduced the concept of the algebra generated by a class of sets and the sigma-algebra generated by the class of sets. Now I will make more precise my last observation. This is, let's say, a lemma which reads as follows. So let's consider a set omega, and let S to be a semi-algebra, and S a semi-algebra of subsets of omega. Now let's denote by A of S the algebra generated by S. Okay. What I claim is that if A belongs to AS, then there exists EJ from J from 1 to N, EJ in the semi-algebra, and A, it's equal to the disjoint union of EJ. Right? So this lemma is telling me that any element of the algebra generated by the semi-algebra S can be written as a finite disjoint union of elements of the semi-algebra. And, well, the opposite direction of this claim, it's obvious, right? If EJ are elements of the semi-algebra, they are also elements of the algebra generated by S, because the algebra generated contains S. Since the algebra is closed by finite intersections and by complement, it's also closed by unions, and therefore A belongs to A, to the algebra generated. So the reversed statement, it's a triviality. Right? So this is telling us that an element of the algebra generated by a semi-algebra can always be written as a finite union, disjoint union of elements of the semi-algebra. So let's prove this claim. So I first prove the reverse statement, which means that, so I'm supposing that A is a finite union of elements of the semi-algebra, and I want to show that A belongs to the algebra generated by S, right? So, as I said, this claim will rely on the following observation. I want to prove that if A, and well, let me give another name for that, if E and F are elements of an algebra, then the union of E and F also belongs to an algebra, right? And this is clear because I can rewrite the union of E with F as, well, the complement of the so let me represent by EC the complement of E. So let me take the intersection of the complement of E with the complement of C and take the complement of that. So you can easily check that these two sets are equal. If A is an algebra, we have seen that it's closed by complement. So since E belongs to A and F belongs to A, E complement and F complement belongs to A. It's an algebra, so it's closed by intersection. So this intersection, it's also an element of A, and A is closed by the complement. So it follows from this identity and from the properties of the algebra A that A is closed by finite unions, right? You can repeat this argument to prove that, in fact, A is closed by finite unions. Well, so let's go back to this claim. I know that A is written as a finite union of elements of the semi-algebra, but the semi-algebra is contained by the algebra generated by the semi-algebra, which means that each of these sets belongs to the algebra generated by S, and therefore the union, and therefore A belongs to the algebra generated by S. Right? So this is the reverse statement. Right? Let me go back here to the statement of the lemma. So one piece of the statement was saying that if A is the union of sets EJ belonging to the semi-algebra, then A is an element of the algebra generated by S, and this is what we just proved. So now let's prove the main assertion of this lemma. Right? We want to show that any element A of the algebra generated by the semi-algebra can be written as a finite union, disjoint union of elements of the semi-algebra. Well, I will first show that if you take the class of sets EJ, so let me define a new class of sets. Maybe let me call that F, not to mix it with the E which appeared before. So I'm defining a new class of subsets of omega. Which is this class? Well, the class of all sets which can be written as finite disjoint unions of elements of the semi-algebra S. Right, let me call that B. So B, it's a class of subsets of omega. And which class is this? Well, all the elements of B are the ones which can be obtained as finite disjoint unions of elements of the semi-algebra. I will prove first that B is an algebra. And then I will prove that B contains the semi-algebra. And if B is an algebra and B contains the semi-algebra, by definition of the algebra generated by the semi-algebra, I will conclude that B contains also A of S, the algebra generated by S. This means that any element of the algebra generated by S belongs to B and therefore can be written in such a way, which is the claim. So, to prove the main assertion of the lemma, what we need to show is that this class of set is an algebra and contains the semi-algebra S. That it contains the semi-algebra S, it's clear, because any element of the semi-algebra can be written as itself. Therefore, B clearly contains the semi-algebra S. So the main point is to show that B is an algebra. To prove that B is an algebra, we have to check the three conditions of the algebra B. So let's check the three conditions. The first one, if you remember, is the fact that omega belongs to B. But this is clear because omega belongs to S, the semi-algebra, and the semi-algebra it's contained in B. So it's clear that omega belongs to B. The second point is that if I take a set A and a set B in B, then A intersect B belongs to the class B. So let's prove this claim. Let's assume, let's take a set A in B and a set B in B. Since A belongs to B, by definition of B, A can be written as a finite disjoint union of elements of this semi-algebra S. By the same reason, the set B can be written as a finite disjoint union of elements of S. Now let's take the intersection of A and B. So the intersection of A and B, well, let me write it with all details. It's just, well, A, it's the union of EJ, and B, it's the union of FK. Now, let's distribute the union with the intersection. So what we get is that this is the union in J and K of EJ intersection FK. You can check that these sets are disjoint 2 by 2, so that indeed we have here a union over sets which do not intersect. On the other hand, EJ and FK are elements of the semi-algebra. And this semi-algebra, it's closed by intersection. So this intersection is an element of S. And therefore, by definition of the class B, this set, which is written as a finite disjoint union of elements of S, belongs to the set B, which proves that A intersection B indeed belongs to B. And this is the second property of algebra, of an algebra. So now we need to prove the third property, which is that if A belongs to B, then A complement also belongs to B. So what we need to prove is that if A is an element of B, then A complement is an element of B. But what do we know when we say that A is an element of B? Well, A then can be written as a finite disjoint union of elements of the semi-algebra. And we want to show that the complement of A belongs to B. So let's consider the complement of A. The complement of A is a complement of this union. Well, but you know that the complement of a union is just the intersection of the complements. So this is E1 complement intersection E2 complement intersection En complement. And we know that each of these sets belongs to the semi-algebra. And by the property of the semi-algebra, we know that the complement of a set in the semi-algebra can be written as a disjoint union of elements of the semi-algebra. This means that E1 complement can be written as a sum from, say, K1 going from 1 to L1 of F1 K1, where f1j belongs to the semi-algebra, right? So this is one of the properties of the semi-algebra, is that the complement of set in the semi-algebra can be written as a finite disjoint union of elements of the semi-algebra. And in the same way, this holds for any of these sets. So let's take AI complement and let's write it as a sum of ki going from 1 to li of fi ki, where again fij belongs to the semi-algebra. And let's replace these identities in this formula. So we have here E1 complement, which is a sum from K1 from 1 to L1 of F1 K1, intersection union, disjoint union. So remember that this symbol means that we are taking the union of disjoint sets. So a union from K2 from 1 to L2 of F2 K2, intersection the disjoint union from Kn going from 1 up to Ln of Fn Kn. And now it remains to distribute this intersection in these unions. So this will be union from K1 up to L1, Kn from 1 up to Ln of F1 K1, intersection F2 K2, intersection Fn Kn. Again, you can check that all these sets, so if you take these sets, they are disjoint 2 by 2 because the Fij are disjoint. If you fix the first coordinate, then you get a family of disjoint subsets. And since these sum are, well, at least one of them is different, one of these first coordinate is different when you take two sets, you can check that these sets are all disjoint 2 by 2. Since each set F belongs to the semi-algebra and the semi-algebra it's closed by intersection, these intersections are elements of the semi-algebra. Therefore, we have just written the complement of A as a finite disjoint union of elements of the semi-algebra, which means that A complement belongs to B as we claimed. We have therefore proved that the class B is an algebra because it contains the set omega, it's closed by intersection and closed by complement. Since it's an algebra and it contains the semi-algebra S, it also contains, by definition, the algebra generated by S, and therefore any element of the algebra generated by S can be written as a finite disjoint union of elements of S, as we claimed. So this proves the lemma. So now that we introduced the concepts of semi-algebra, algebra, and sigma-algebra, we can start to investigate the functions defined on this class of sets. So what we will do is we'll introduce two natural definitions, and then we'll investigate the properties of these the functions satisfying these conditions. So the first definition is the following. Well, let's assume that we have a class of sets of subsets of a set omega, and again you can keep in mind that omega, say, it's the line, or r to the power n. So let's assume that we have a class of subsets, and that this class contains the empty set, and that we have a function mu, which is defined on this class, and takes values in r plus union plus infinity. So I will say that mu is additive. So here is the important notion. So mu will be additive if mu has two properties. The first one is that mu at the empty set, it's equal to 0. So remember that we are assuming that the empty set belongs to C. And then that, this is the most important one, let's take E1, E2, En in C. Let's assume that they are all disjoint 2 by 2. So let's call E the union of Ej, j from 1 to n. And let's assume that E belongs to C. So you see that if C is not an algebra, there is no reason why this union should belong to C, but I'm assuming here that E belongs to C. So I will say that mu is additive if mu of the empty set is equal to 0, and if I take any such collection, then mu of E, it's equal to the sum of mu of Ej, right? So if I can express any set E in C as a finite disjoint union of elements of C, then mu of E should be equal to the sum of mu Ej. So I'll say in these two cases, if mu satisfies these two conditions, that mu is additive. So this is a definition. Now let's see, a trivial observation. Trivial observation is the following. Well, let's assume there exists a set A in C such that mu of A is finite. So assume that there exists one set whose value under mu is finite. Then I can always write A as the union of A and the empty set. It's clear that A intersection empty set is empty. Therefore, by the second property of mu of A, it's equal to mu of A plus mu of the empty set. Well, but since mu of A is finite, we conclude from this equation that mu of the empty set is equal to 0. And this means that if there exists a set for which mu of A is finite, then the first condition which we impose is redundant, follows from the second condition. Okay, so just keep that in mind, that this condition is not very important if there is a set which has finite, whose value under mu is finite. The second observation is that, let's go back here to the definition, is that the natural class C would be an algebra, because we are here taking finite unions. So it's natural to define mu in a class C which is closed under finite unions, which is, as we have seen, an algebra. But this definition can be made in any class C. It can be made, for instance, in a semi-algebra, and we will use that later. So before we go through examples, let's just make a second observation, which is also very simple. Let's assume that we have a set E which is included in the set F. Well, there are two possibilities. Either mu of e it's equal to plus infinity, or mu of e is finite. So let's see what happens under this first condition. If we assume that f minus e belongs to C. So I'm here assuming that we have a class C, and so we have a class C, and we have mu, which is defined on this class C in R plus, taking values in R plus union plus infinity, and that it's additive. Right? So let's consider the case in which we have three sets, E, F, which belongs to C, and let's assume that E is included in F, and that F minus E belongs to C. As I said, we have two possibilities, either mu of E is plus infinity or mu of E it's finite. Let's see what happens in these two conditions. We can always write F as the set E union F minus E, because E is contained in F. Clearly, these two sets are disjoint. If mu is additive, we can just write that mu of F it's equal to mu of E plus mu of F minus E. Right? Because mu is additive, and we are assuming here that F, E, and F minus E belong to the class C. Well, if mu of E is equal to plus infinity, since mu takes only non-negative values, we conclude that mu of F has to be also equal to plus infinity. So in this first case, we obtained that mu of F it's equal to plus infinity. While in the second case, if mu of E is finite, we can subtract mu of E on both sides and conclude that mu of F minus E it's equal to mu of F minus mu of E. So if mu of E is finite, mu of F minus E is mu of F minus mu of E. In both cases, we conclude that mu of E is less or equal than mu of F. Right? Because in the first case, they are both equal to plus infinity, while in the second case, mu of F it's equal to mu of E plus something which is non-negative. So in conclusion, if E is contained in F, we always have that mu of E it's less or equal than mu of F. And also, if mu of E it's finite, then mu of F minus E it's equal to mu of F minus mu of E. So now I want to give you some examples before we proceed. The first example is, well, it's what we'll call a discrete measure. So we have a set omega, and let's assume that we have a family of points, xj, of points of omega, and a sequence of non-negative numbers. So I will define a function mu. So let's say that we have a class of subsets of omega, and I will define for A in C mu of A as, well, I will sum Pj always then then xj belongs to A. So I will sum pj if xj belongs to A. So this is the indicator function of the set A, which means that this is 1 if xj belongs to A, and this is 0 if xj does not belong to A. Therefore, here I'm summing over all j's for which xj belongs to A, and I'm summing pj. And this is the way I'm defining mu A. And you can check that indeed mu, it's additive. The second example relies on the definition of sigma additivity. So before I give it to you, let me introduce the notion of sigma additivity. So sigma additivity, it's very similar to additivity, but we will require something slightly stronger. So again, we have a class of subsets of some set omega. We will assume that the empty set belongs to C, and that we have a function mu, which is defined on C, and take values in R plus union plus infinity. So I'll say that mu is sigma additive if two conditions are fulfilled. As before, I will require that mu of the empty set is 0, and as a second condition, now, instead of the union of a finite sets, I will consider countables union. So let's take aj in C. Let's assume that they are all disjoint 2 by 2, so that aj intersection ak is equal to the empty set if j is different from k. And let's assume that E, which is the union of these sets, belongs also to C. So if this is the case, I will require mu of A to be equal to the sum of mu aj. Note that all these sums are well defined because I'm always assuming that mu takes only non-negative values. So in the previous definition, in this one, well, what might happen is that this sum is plus infinity, but it's certainly always well defined. So I would say that mu, it's sigma additive if we have this identity for all class of sets satisfying these three assumptions. So now let's see an example of a function which will be additive but which won't be sigma additive. So let me give you a second example. So I will consider set omega to be the interval 0, 1. And I will define, so C will be, let's say, a class of sets of the form A, B, where A, it's greater or equal than 0, smaller than B, which is smaller than 1. So this is a class of sets, of subsets of omega, and I will define a function mu. Well, let's include in this set the empty set, and I will define mu on C as follows. Well, mu of this set AB will be, well, if A is equal to 0, So if I'm taking 0b, b strictly bigger than 0, then I will define mu of ab to be plus infinity. And now if a is strictly positive, I will define mu of ab as the length of this interval, which is b minus a. Okay. So I leave it to you to check that this function mu, it's additive on C. Right? If you can write AB as a finite sum of AJ, BJ, sorry, it's closed on the right. So what I claim is that if AB it's equal to this finite union of intervals, then I claim that mu of AB is equal to the sum of mu AJ, BJ. Right? This will be infinite if A is 0. If A is 0, there is one j for which AJ is 0, and therefore we will have infinity equal to infinity if we compute mu on both sides. While if A is strictly positive, this will be the length of the interval AB, and this will be equal to the sum of the length of these intervals. So I leave it to you to check that indeed mu is it's additive. But it's mu, what now I claim that mu is not sigma additive, well, because I can write the interval, say, 0, 1/2 as a union of, so if I take a sequence xj decreasing to 0, so this means that xj it's strictly bigger than xj plus 1, which is strictly bigger than 0, and that xj it's converging to 0. If I take x1 to be 1/2, and I consider the intervals xj plus 1, xj, what I claim is that 0, 1/2 is equal to the union of these intervals. This interval and all these intervals belong to the class C, but when you apply mu to 0, 1/2, what you get is plus infinity, while when you apply mu to xj plus 1 xj, what you get is the length of this interval, which is xj minus xj plus 1. If you sum that over all j, what you get is the total length of this interval, which is 1/2, which proves that if we apply mu, we don't get that mu 0, 1/2 it's equal to the sum of mu xj plus 1 xj, and therefore that mu is not sigma additive. So this is an example of a function mu, which is additive, but which is not sigma additive, and we will use this example later on.